Hello and welcome to another WJEC A level physics question. This was question 3 from June 2014, Unit 5. It's a capacitors question, and capacitors are now found in Unit 4. So what we've got here is a parallel plate capacitor connected to a 128 volt supply. The area of the plates is 0.0488 meters squared, and the plates are separated by 0.059 millimeters in a vacuum. We're going to calculate the charge stored in the capacitor, so we're going to end up by using Q equals CV, but we don't know what the capacitance is, so we're going to use the parallel plate capacitor formula, C equals epsilon naught A over D, to first of all calculate the value of the capacitance. Epsilon naught given in the data book is 8.85 times 10 to the minus 12. Now the area is fine, it's 0.048 meters squared, so no need to worry about any kind of conversion there. But what we've got to be careful of is that the separation of the plates is in millimeters, so we've got to remember to put a 10 to the minus 3 in here, otherwise we're not quite going to get the right answer. So let's put those values into the calculator. And we end up with a capacitance of 7.32 times 10 to the minus 9, or 7.32 nanofarads. Now we can calculate the charge stored. Charge stored is the capacitance, 7.32 times 10 to the minus 9 times 128 volts, potential difference. And that will give us 9.4 times 10 to the minus 7 coulombs, or if you like, about 937 nanocoulombs. 937 nanocoulombs. Yeah, it's a charge that we wanted there. Use our answer to part 1 to calculate the energy stored in the capacitor. So we've got a choice of formulas: half CV squared, half QV, half Q squared over C. Doesn't really matter which one we use here. I'm going to go for half CV squared. So we got half times the capacitance of 7.32 times 10 to the minus 9 times V squared, where V is 128. So let's put those into the calculator. And that will give us very close to 6 times 10 to the minus 5. So let's call it 60 microjoules, 59.97 and so on. So near enough 60 microjoules. To calculate the field strength between the plates, we simply use the relationship that E is V over D. So we got 128, and that separation was again millimeters, 0.059 times 10 to the minus 3. Which gives us about 2.2 megavolts per meter. Now the alternate unit here would be, of course, newtons per coulomb, but because we've used volts and meters, it's more common to use volts per meter here. For the next part of the question, after the capacitor is charged, it's isolated from the power supply so that the charge remains constant, and the plates are pulled further apart. Explain what happens to the capacitance of the capacitor. Well, from C equals epsilon naught A over D, if the area hasn't changed and epsilon naught is a constant, then C is inversely proportional to D. So as we've increased D, the capacitance will decrease. Now as for the energy, we've got to be very, very careful here, because you can get wrong conclusions by using not necessarily a wrong equation, but not the best equation here. So let's think the charge is remaining constant. So what we want is the formula that's got charge in and also capacitance, because we know what's happened to the capacitance. The capacitance has decreased. So what we've got here is the equation U equals a half Q squared over C. And since Q is constant, this will tell us that U and C are inversely proportional, so U will increase. If, for example, you'd used U equals a half CV squared, you might have thought that U was directly proportional to C, but the problem here is that V is not constant. The potential difference across the plates will change with the separation. So here we've used U equals a half Q squared over C. Q is definitely constant, so therefore U is definitely inversely proportional to the capacitance. To explain how energy is conserved in this case, well, those plates are oppositely charged. There will be a force of attraction between them, so you have to do work in separating the plates. You actually have to apply a force to separate the plates and increase the distance, and therefore you will have done work. Remember, work is force times distance. So what we're going to say here is that the extra energy, and that's an important word there, the extra energy stored is equal to the work done in separating the plates. Now the reason why extra is important there is if we just left it as energy stored is equal to the work done in separating the plates, we're sort of forgetting that there was energy stored in the capacitor even before we started separating the plates. So thank you very much for listening. Please remember to like and subscribe, and feel free to ask any questions you like about this video. Goodbye.